So what we are actually doing is we are kind of following the same line of argument that we used in order to show that from a uniform convergence result we get learnability depending on VC dimensions. So let me just try to draw the correspondence between what we've already seen in the case of PAC learning to what we are seeing now with respect to non-uniform learning. So if we have here what we did with respect to PAC learning or to agnostic PAC learning, and I want to compare it to what we are doing now with respect to non-uniform learnability. So when we talk about agnostic PAC, we showed the learnability in two steps. The first step was a convergence bound, which it does is it kind of relates LS of H to LD of H. That was the first step. And then after we had the convergence bound, we were looking at a given algorithm or a given learner. And the learner was the ERM learner. So here the next step was we were looking at a given learner. In our case, it was the ERM learner. And we bound its error or its loss. So in the case of PAC, the convergence result was the result that's saying for every H in H, so it all starts with all these big kind of building up, just the laying down the setup. So we say that for every epsilon, for every delta, for every H in H, for every probability distribution P. I'm not going to repeat all this because I want to focus on the point where things differ. But so here we have all kind of for everys, right? For every P, for every epsilon, delta, and so on. And then we got a convergence result. What was the convergence result? The convergence result was that the gap between LS of H and LP of H is at most epsilon with probability is greater than epsilon with probability less than delta. That was the uniform convergence result. So if M is big enough, then some formula, then we got this result. Now that we had this uniform convergence result, we said this implies success of ERM. So the conclusion was that if A is an ERM learner, then again, all those for alls, for every probability distribution, every epsilon delta, and so on, we get that the loss with respect to P of A of S is at most and that was for every, again, for every H in H, is at most the loss with respect to P of this H plus epsilon. And that was, again, for large enough, for M greater than MH of epsilon over 2 delta, and this was with probability at least 1 minus delta. Okay, so I know that it may be difficult to read, but it should be familiar. I'm just reminding you what was the result. And I'm saying that we first had the uniform convergence result. Then we proved that if we have this uniform convergence, which was the samples, most of the samples, at most delta of them just failing it, most of the samples, the estimate of the error according to the sample is close to the true error, then we can use ERM. And if we pick a sample big enough such that this gap is at most epsilon over 2, then the error of the ERM learner will be bounded by the error of every h in h, or the minimum over all of them, plus epsilon. So what I'm saying, we went in 2 steps. One of them was a uniform, completely statistical result, uniform convergence result, and then the conclusion was something about the behavior of an algorithm. This is the error of what the algorithm chooses. And this is something that's saying for every h, we have this kind of similarity between this loss and this loss. But this is about how the algorithm behaves. And since we had an algorithm that has this behavior, we knew that the class is learnable. So now we want to repeat the same 2 steps with respect to non-uniform learnability. We want a convergence result, and then we want to have an algorithmic paradigm that will take advantage of this convergence result. And the convergence result is what we saw last time. So last time we only did the convergence result. The convergence result was, again, so there was a lot of preparation here. We said that H is a union over n of HNs, and each HN has uniform convergence property with some function mn of epsilon delta. And we had this W, we had this function W that goes from natural numbers to 0, 1, and the sum over all n of Wn is at most 1. So we had all of those setup, building the setup. And then we said that we get now a convergence, a uniform convergence result. Right? And the uniform convergence result that we got here is that, again, for every probability distribution P and every M and every delta and every H in my class H, what did we get? We got that if we pick S of size M, so the probability over S being picked by P to the M, that, and here we had LS. So the way I wrote it is that instead of having the for all H here, I had here there exists an H that violates it. But it's the same thing. Saying for every H we are doing well is the same as upper bounding the probability that there exists a violating H. So there exists an H that what does this H violate? Such that the gap between LS of H and LP of H is bigger than something. See, it's exactly what we have here. But the something was slightly more difficult, more complicated. It was this epsilon of n of H of M, and here we had W of n of H times delta. This probability is less than delta. So that was the result that we saw last time. Yes? Yes, I will remind everything. So n of h, you see, h comes, this is the existent h in this capital H. And the capital H has layers, HNs. So n of h is the minimum n such that h belongs to Hn. Since h belongs to the union of all the Hns, for every such h, I have some homeland, Hn, where it came from. And I look at the minimum n such it belongs to Hn. So that was one thing we needed to describe here. And here we needed to describe what is this epsilon. And here I have some number, and here I have two parameters, right? So I have to explain this also. So what is epsilon of some number n and some sample size m and some delta? I mean, the delta is going to be this number, but what is this? This is the minimum epsilon such that the function m n of epsilon delta is below m. Or in other words, what are we doing here? This is the best approximation that I can guarantee with m many samples. I have my sample size is fixed. I fixed my sample size. So if I fix my sample size, I can view this function as telling me for a given sample, this tells me if I fix epsilon and delta, what will be the sample size. But I can reverse it. I can ask for a given sample size and given delta, how much epsilon I can tolerate. How small is the epsilon that I will be able to tolerate. And that's this function epsilon n of m and delta. So it's the minimum error that I can guarantee if I'm giving m points. Minimum error that I guarantee given n points in the class Hn. So this result is the exact analog of the classic result that we had, or the basic result that we had on uniform convergence or on the existence of representative samples. Because this just said the sample, I mean, this says the sample is not representative, or the opposite is saying the sample is representative. So this is saying the sample is representative, but the question is representative to which extent? So this is just putting in context what we did last time. And it would be better that you ask questions than you just give up at this early stage of the lecture. I could rewrite this as something completely similar to this one. I could rewrite this one as saying what happens is that the probability over S coming from P to the M, that there exists an H such that L P of H minus L S of H is greater than epsilon, this probability is less than delta. This is just rewriting the same result. So now we see how similar are these two results. The only difference between these two results is instead of having a fixed epsilon, I have here this complicated epsilon that depends on where did the h come from. If h came from a class with a large n, then this epsilon is going to be a big number or a small number. What do you think? If epsilon came from a class with high n, if h is coming from n with a very big number, will this epsilon be big or small? What do you say? It'll be big. Why will it be big? It will be big for two reasons. I mean, one reason is not clear. I mean, what is this Mn? What is the uniform rate of convergence for this class? But the reason it will really push it to be big is this here. W of this n is going to be a very small number, because the w's of all the n's should sum up to 1. If I have a sequence of numbers that sums up to 1, then high members, found members in this sequence must be very small. So this is going to be a very small number. When I multiply delta by a very small number, I get an even smaller number. So I require here a very high confidence. The probability of error should be very, very small, the probability that I'll miss. So if the probability that I'll miss is very, very small, and m is fixed, I cannot guarantee it for a small epsilon. Epsilon should be very loose. Does it make sense? So what is the next component that we have to come up with now? We want to prove that classes that are unions of finite dimension classes, classes of this form, are non-uniformly learnable. This just gave me a statistical result. What do I need in order to show that it's learnable? What does it mean to be learnable? What are we missing here? Yes? I'm missing an algorithm. Because learnable means there is an algorithm that can do the job. So we miss two components. We miss the algorithm, and we miss this function. You remember, we are looking for a function m, h of epsilon, delta, and h. So we have to define this function and show an algorithm that with so many examples will successfully learn every h. So now we are missing this second component, which is the learner. In the case of PAC, the learner was empirical risk minimization. Now we need something analogous to the empirical risk minimizer. Before I present this analog, I want to mention that what we have here, I can rewrite this bound, or a conclusion of this bound. This bound just tells me L of the loss according to S is close to the loss according to P. But I can rewrite this bound as an implication of this bound is that the bound, this bound, implies that with high probability, the loss with respect to the true distribution of H is bounded by the loss with respect to the sample of H plus this epsilon NH M W of NH delta. I'm saying if those two things are close to each other, then LP is upper bounded by LS plus this looseness. And now, once we notice this, so this is what we want to minimize. We want to show that we are going to pick an H with a small arrow, with a small P arrow. So this bound tells me the P arrow of every H is bounded by this. So this dictates my algorithm. My algorithm, yes?
Why do we want to, like, what's the motivation behind upper bounding it rather than lower bounding it?
What is the motivation behind upper bounding this? I want to output some h, and I want to make sure that this h has small probability, a small error, right? I want to put an h with a guarantee that has small error. So I want to say my true error of h is not big.
Oh, sorry, I got the SMP backwards. That makes total sense.
Makes sense, right? Okay. So now what is going to be the algorithm? The algorithm is going to be, this thing, this guy is an upper bound on my error. So I'm going to pick an h that minimizes this upper bound. Okay? Yes?
So this W, the weight function, how do we know that this weight function is good enough in comparison to some other weight function?
How do we know that the weight function is good enough?
Yeah, we just found there can be many weight functions which is upper bounded by 1.
There may be many weight functions, right? And every weight function that sums up to 1 will be good. That's what this theorem tells you. The algorithm will depend on the weight function that you choose. But every weight function that sums up to 1 will work. So here is the algorithm. So you see, we have this upper bound for every h. So I can, if I'm giving any s, so if we're given any training sample S, then if I have here, say, h1, h2, h3, h4, I'm going over all h's in h. And for each of them, I'm looking at what is the real loss of h. So what this tells me is that here is an upper bound. The real loss of h, for every h, I can draw this kind of guy, this guy. This is the bound. For h. For every h, I know that the true loss, so what I know is for every h, the true loss will be somewhere below this bound. I don't know what the true loss exactly is going to be. And I have to pick an h. So which h is a natural choice to pick here? You see, I know that the arrow is at most this. I don't know, maybe the real arrow, I don't have colors. Okay? Maybe the real arrow behaves completely differently. But I know that the real arrow is always below this bound. So which h is a natural choice to pick? Yes?
The minimum.
The minimum of what? The one that minimizes the bound. Okay? So I will pick the one that minimizes the bound. Here, maybe. This h that minimizes the bound. It's not necessarily the best h. Maybe there is an a. Maybe I have an h that this h2 has this arrow, and it is better than the error of this guy. But I don't know it. All I know is that this is the only guarantee that I have. So the best I can do is to minimize the guarantee, to minimize the upper bound on my error. And that's what I'm going to do. So this is called the structural risk minimization. OSRM. And this is saying just pick the h that minimizes this bound. So let A of S be any minimizer, any h in H that minimizes this bound. Right? So I want to minimize this bound here. I want to minimize LS of H plus this epsilon of N of H M W of N of H times delta. This is going to be my algorithm. What does this algorithm need as an input? The algorithm that I have here, what does it take as input? The input to this algorithm is some sample S. I'm giving a sample S. So I know what is the size of my sample. And I'm giving some delta. Delta should be given as an input to my algorithm. Given S and delta, I can calculate for every H this bound and pick the H that minimizes the bound. So, in conclusion, so a structural risk minimization algorithm is given some training sample S and a confidence parameter delta, and picks H to minimize this bound, arrow bound. Yeah, and by saying this, I mean this thing. That's what you want to minimize. Just note that if someone gives me S, then I already know what M is, and delta is given to me, so I can really calculate this guy. To calculate this guy, I need the functions, the uniform convergence functions for each of the Hns, and I need M, and I need delta. And I have all of those ingredients. So for every H, I can calculate this bound. For every H, I can estimate its empirical loss. So I can calculate these two components and pick the H that minimizes the sum. That's going to be the algorithm that is the analog of the ERM algorithm. So the ERM algorithm just said minimize the empirical loss. But now we are saying minimize the empirical loss plus a penalty term. If you are picking a very complex H, there's going to be a big penalty term here. So you have to trade the loss that this H gives you against the complexity of this classifier, which is a very natural thing to do. I mean, once we begin to see what this algorithm does, we can realize also that it's a very natural thing to do. Okay. So why is it a natural thing to do? Because if I have some phenomena, some physical phenomena that I wish to explain. So if I have a very simple explanation, it's likely that this explanation will not be precise. It will only approximate what I'm seeing, right? If I have a very complex explanation, then the problem is that I may be overfitting. So maybe very roughly, think of it this way. Assume that I have some kind of measurements. It's not exactly this setup, but it's just to give the flavor of what we are doing here. I have some kind of measurements. So I have different x's and I have x, y, and I'm doing physical measurements. I'm measuring, I don't know what, 2 parameters of some phenomena. Say I don't know which phenomena you care about, but let's say that this is the weight of a mother and the weight of the baby when the baby is born. So I'm looking at many babies, and for each of them I can draw some kind of what was the weight of the mother and what was the weight of the baby. And now I'm trying to find a formula that best explains or predicts the weight of the baby as a function of the weight of the mother. So one way, I can take a very simple explanation, say a very simple explanation, say the weight of the baby is this. This is the function. And this simple explanation will a lot of time have a lot of error. I can also take a very complex explanation and say, this is my explanation. I don't know what. And this doesn't make any error. It meets all the points exactly. So this is an explanation for which LS of H is 0. But why it may not be a good explanation? Because the H that I pick here is very complex. Very complex means it came from a very high Hn. So I'm paying a lot of penalty to protect against overfitting. Maybe this explanation, although it looks so nice on the sample, it doesn't have much statistical validity because it's too complex. It could have fit all the points exactly for no statistical reason. So I'm doing a trade-off between the accuracy of my explanation on the data that I see and the complexity of my explanation. And that's exactly what the SRM paradigm is suggesting in a very precise quantitative way. Minimize the sum of how well you explain the data plus penalty for picking a complex assumption. Does it make sense? The more complex assumption, the smaller I can make the empirical error. But the higher is the risk that it doesn't generalize. So I hope that out of all those confusing parameters and crazy formulas, the principle should become clear. And this is really the principle that people are using in real machine learning. ERM, the reason we're not using ERM in machine learning is that we cannot restrict our attention in advance to a class of finite VC dimension. That's too restrictive. It wouldn't explain well the phenomena in the world. The other extreme is just say, pick any function that fits the data well. But then we are running into the no free lunch paradigm problem. We are going to overfit. And this is some kind of the practical compromise. We have a hierarchy of explanations, and we trade our explanation against its success against its complexity. So what do we need to prove now? I guess we don't want to see any more proofs. The next claim that I have to show you is, why is this a good algorithm? Intuitively, it makes sense. But formally, why is it a good algorithm? And here we can have a theorem. And the theorem tells me that with this algorithm, every class which is a union of finite VC classes is non-uniformly learnable. Right? So here I have a theorem that tells me this algorithm actually does the job and proves that every union of HNs like this is non-uniformly learnable. So what is the theorem? The theorem it just says that given any H which is such a union, where each Hn has finite VC dimension or is has the uniform convergence property with some function mn of epsilon delta, and given any w that goes from n to 0, 1, such that the sum over all n of wn is at most 1, any SRM algorithm is a successful non-uniform learner with sample complexity right? I need to give you this m h of h epsilon delta. That is the kind of guarantee that we need in order to show non-uniform learnability, that there is such a function. Right? What is this function going to be? I have to look at my notes to make sure that I'm not missing anything here. So the function is m of nh. Remember, we have here for every n, we have this function m of n. nh is the n from which h comes, of epsilon over 2. And for delta, I take w of an h times delta. So I give you this function, which is a function of h, epsilon, and delta. In what way it depends on h? It depends on h because h determines n of h. H determines which class did I come from. And the epsilon half that we see here is exactly the same epsilon half that we saw in the case of PAC learning. I will explain in a second why is it epsilon half and not epsilon. So now I need to prove it. And somehow I have this feeling again that if I'll get into too much technical details, I'll be just talking to myself. So let me just explain the proof rather than write concrete formulas. So the trick is, what do we have to show? We have to recall what do we have to show. What does it mean that this is a good learner? We need to show that for every h epsilon delta and every p, if m is greater than this m h of h epsilon delta, then the probability where S is picked from Pn that something will go bad. So that what is something going bad is that A of S, what the arrow, the true arrow of what we pick, what is being bad? Being bad, it is going to be bigger than the true arrow of the H we are competing with, plus epsilon is less than delta. That was our definition of non-uniform learnability. For every H, I can guarantee that it's unlikely that my error will be bigger than the error of this H, plus epsilon. Unlikely means less than delta. And this was for a specific H because the M, the sample size, is determined by this H. For every H I want to compete with, there will be a different sample size. So that's what I have to show. And the only thing I have to just make sure is that when I put here the sample size that I picked, what I will get here is epsilon half. So if I substitute for this M, if I substitute into this M what I now defined as MH of epsilon of H epsilon delta. If I substitute it for this M, the epsilon that I will get here is epsilon over 2. Again, I start with an epsilon and delta here. I calculate this number and substitute it here and compute this epsilon. It's going to be epsilon over 2. So this is something I want you to check. Make sure that when I take the MH that I have here, where was it? Where was our definition? This one. When I take this number MH and I substitute it for the M there, I will get as epsilon the epsilon over 2. You see why? I mean, anyway, I'll leave it to you to see why. It's just a matter of following the definitions without getting confused along the way. So I'm just picking MH big enough to make this equal epsilon over 2. Why will it finish the job for me? Because now my algorithm minimizes this bound. So my algorithm LP, the true error of what my algorithm picks, is at most, it minimizes this bound. So it is at most the value of this bound for the H that I want to compete with. So it is at most LS of this H plus this epsilon of this H, epsilon of NH. I'm minimizing this bound, right? So I'm just copying this bound. Epsilon W of N of H times delta. This is just, I picked an H star that minimizes this bound over all H's. So in particular, it's below the value of this bound for the H that I want to compete with. I'm trying to compete with a given H. My algorithm takes the minimum over all H's of this. So in particular, it competes with this H. But the problem is that this is LS, and I want to compete with LP. Oh, sorry. This is just our LS of our algorithm. This is just by picking the RSM, SRM minimizer. Right? But I know that LP of my S, A of S, will be at most LS of my A of S plus this epsilon that we just said is at most epsilon over 2. This is by our statistical guarantee. Yes?
Should that second epsilon be M?
Should this?
In the brackets?
Oh, this should second epsilon should be M, of course. Okay. This is going to be how much for you? How? Third or something? Okay. Yeah, this is M. Okay, so what I'm saying is that what we care about is the true error of what our algorithm outputs compared to the true error of this H. Anyway, so this is bounded by this. The true error of my algorithm will be this plus at most epsilon half, because the value that we get here is epsilon half. Now I'm going to take this and put here. So I'll get that LP of A of S is at most, now I'm putting this here, LS of H plus this epsilon n, all of this guy here, which is at most I'm losing one of my epsilons over 2 factors is I'm getting too much by 1 epsilon over 2 factor. So what I'm getting, the true error of my algorithm is bounded by the empirical error plus this epsilon half. This empirical error is bounded by what I have here. So I'm getting here epsilon half plus epsilon half. But if I want to compare it to LP of H, because this holds for every H, I get here, somehow I got 3 halves instead of just 2 halves. I get here LP of H plus epsilon half plus epsilon half plus another epsilon half, because, again, for every H, this gap is at most epsilon half. So in particular, it holds for the H that I'm competing against. So for some reason, I got 3 halves epsilon instead of epsilon. But it's good enough to show that the algorithm learns well. Okay. So you just have to go over, kind of iron out my confusion here, and one of the 3 epsilon halves will go away. But the argument that we see here is exactly the same argument that we showed for ERM working. ERM should work with sample size that guarantees that the gap here is epsilon half, and it's exactly the same argument. So what we proved is that our SRM paradigm can really learn with this sample complexity. It does non-uniform learning with a sample complexity that depends not only on epsilon delta, but also on how complex is the H that you are competing against. OK, so this ends our proof that if a class is a union of finite VC classes, then it is non-uniformly learnable. So what I want to do now in the remaining 25 minutes of this lecture is to show you one very concrete and very kind of natural, useful implementation of this SRM principle. OK, any questions about what we did here? Yes?
Was this
Okay, so that's a very good question. Is it possible for my capital H to be the set of all functions? And it's not that I expect you to know the answer, but I gave you the answer last time. It's just a question of, do you remember what I said last time? Yes?
I think it's no, because you can't divide the set of all functions to a union.
Right. I mean, the answer is no, and it's no because I cannot divide the set of all functions over an infinite domain to such h n's of finite VC dimension. And why I cannot do it, I promised you that there will be a bonus in the next assignment. So it's not that I showed it to you, but I stated it and said that I'll give it to you as part of the assignment. So if you have an infinite domain, if you have a finite domain, you can always present it as such a union. But the problem is, so every finite domain is non-uniformly learnable. The problem is that your required sample size may be more than having to see all of the points in the domain. If it's a finite domain, this kind of non-uniform learnability becomes vacuous, because it just said there is a sample size that will suffice. The sample size will be see every point, see all the points. Then you can learn. So it becomes really interesting when the domain is infinite. And when the domain is infinite, I cannot present all functions in such a union. Yes?
What's your note above the inequality on like the top right most equation on the board? It's like by picking the SRM something.
Minimizer. By picking the SRM minimizer. The SRM picks the minimizer of this quantity. A of S is an H that minimizes this quantity over all H's. So in particular, it beats the given H that we want to compete with. That was what we said here. The SRM picks a function that minimizes this sum.
And does your extra epsilon over 2 come from the fact that you replaced an LS of H with LP of H plus epsilon over 2 instead of minus over epsilon over 2?
No, it's always, whenever I do something, I'm losing a fraction, an epsilon over 2. You see, all I know is that the absolute value is bounded by epsilon over 2. So if I'm taking the pessimistic view, each time I replace one of them by the other, I'm losing an epsilon over 2.
Okay, so it doesn't really matter which direction.
Yeah, it doesn't matter which direction, because all I know is that the absolute value is bounded. Okay, so we have the notion of non-uniform learnability. We proved that non-uniform learnability is equivalent to having the class represented as a union of finite VC classes. Now I want to show you some concrete implementation of this, which has its own merits. It's really an interesting implementation. So the point that I want to talk about is called description length. And this is something that really has both practical and philosophical implications. So this is called minimum description length learning. Minimum description length, MDL, learning. And the idea is that if I have a collection of hypotheses, I want to describe every hypothesis. I can describe every hypothesis either as a program. So we're given some collection H of classifiers. So classifiers are some f's that go from some domain x to, say, +1, -1, or something like that. That's a classifier. So I have a collection of classifiers. I want to describe them. So a description language for H. What is a description language for H? I want to pick a concrete way of expressing every such H. Now think of it, if x is infinite, I cannot tell, if x is finite, I can describe a classifier by giving you a table. For every x, what will be the label? But if x is infinite, I cannot give you such a table because the table will be infinite. So I want to pick a way of describing those h's. So description language will be, I will just denote it by a hat. I don't want to put it L, because L for us is a learner, and L for us is a loss. So L is already too loaded. So it will just be a hat. That's a description language. What does a description language does? It takes functions from H, and to each function, it describes it by a binary string. So it goes into the set of all binary strings. So it's the union over m goes from 0 to infinity of 0, 1 to the m. So what it does is it takes every function. So for each h in H, H hat is a binary string. Which it could be, you can think of it as the code of a program that calculates H. So if every H is a program that given X calculates 0 or 1, and I have a code for the program, so this description could be the code of the program. But even when I'm telling you that this description is the code of the program, I still didn't determine this description uniquely. Why not? Even if I tell you H hat is going to be the code of a program for H. Yes?
There are many such programs.
There are many such programs, and I didn't tell you which is my programming language. Even if I fix the programming language, there are many such programs that will calculate the same function. But I didn't even tell you which programming language to pick. So we are being very abstract, and we're just saying for every H you pick a string, that's a description. OK? And now what we want to do is to say that we can do minimal structural risk minimization with respect to this description length. So we are going to define, we want to define a function. So we wish to define a weight function that is monotonely decreasing with the length of the description of H. So I want to define, I will pick W of H to be 1 over 2 to the length of the description of H. So now, before we talked about W of n, but it's the same that I have a W assigned to every H, as long as the sum is at most 1. And now we're going to do, so now I want to say I can learn any H when I'm using this weight function. And there are two issues here to look at. One of them is, why is this a legitimate weight function? And the other is, what is the meaning of such learning with respect to this weight function? So let us first look at the Well, let me say something. Before I describe why this is a legitimate weight function, let me just say what will be the implication of using such a weight function in SRM. So what will SRM do when applied to this function W? Yes?
So the value of improving the loss by a factor of 2 is just as good as decreasing the size of the binary string?
Right. So it will just say, I mean, without getting into the calculation, basically what we are going to get here is that we're going to say it will turn out, if we do the calculation, that it will just minimize given a sample, training sample S, and given delta, pick H that minimizes. Now we need some calculation to get to this formula, but let me skip the calculation, just give you the formula. It's just a straightforward calculation. What we want to minimize is LS of H plus, and what we'll have here is square root of the length of H plus ln 1 over delta divided by M. So when we do the calculation following the SRM paradigm, what we will get here is that exactly what we want to minimize is some trade-off between how much error I make and I'm paying a penalty. The penalty is more for H's that are complex. What's a complex H? A complex H is H that has a long description, or H that has a long program to compute it. So this is a kind of saying you want to trade the complexity of H. Now the complexity of H is very much more crisp. The complexity of H is how many bits did I need in order to write a program for H. And I want to trade the complexity of H for the error that it makes. So if I want to tell you here is the program should be on x1 do this, on x2 do this, on x3, if I give you just a table, then if I just give you a table and I tell you h of x, the function h is described as follows. H of x1 equals 0. H of x2 equals 1. H of x3 equals 0. And so on. If I describe h in such a particular way to fit the sample, for every element of the sample, what will be the length of h? How many bits will I need to describe my h that fits the sample perfectly? What? No, just the sample size. For every point, I have those bits. Yeah. Just the sample size, right? So I'll have m here. So here I'll have m over m. So I'll have a guarantee that my error is at most 1, which is a very reliable guarantee, but it's completely useless. Right? So if I describe something which specifically tailored to fit the sample, this bound will tell me this is 1. It is meaningless. When will I begin to gain something? When I have a description which is smaller than telling you exactly how you should behave on the sample. So this is going to be the SRM algorithm applied to the description length. And this idea, and we know that we also have a guarantee. We have a guarantee that this algorithm, we know by our previous theorem that this gives us a very nice, that's the error, the loss of this A of S is going to be at most for every h h in h, the loss is going to be bounded by this, ls of h plus the square root of the description length of h, ln 1 over delta divided by m. That's what we proved. We proved that this is really an upper bound on the error that you will make if your algorithm minimizes this. Okay? So we have a justification for an algorithm that is trying to pick the minimum description hypothesis that fits the data. That's why it is called minimum description length learning. Pick a hypothesis of minimum description of the shortest, most compact description that fits the data. And this kind of minimum description length algorithm really works in practice. But before we run it, what do we have to fix? If I want to run such an algorithm, what do I have to fix? What do I have to choose, to pick? If I want to run such an algorithm, you have a class H of classifiers, you get a sample, you want to run this algorithm. What do you have to fix in advance? The weight function, but in our case, the weight function is a description language. I have to fix the description language in advance. But people run this algorithm. I mean, I think that Ming Li, there's a professor in our department, he has a whole company that is based on running such an algorithm with respect to fixing some programming language and picking a shortest, the H with the shortest program in this programming language for describing your phenomena. So he has a question answering program that you can ask it questions and it will give you answers automatically, and it's really based on this idea of minimum description length. Anyway, before we can, there are two comments that I want to make. One more philosophical comment and then show you the mathematical code that we are still missing. So the interesting philosophical comment is that by discovering this minimum description length paradigm or learning algorithm, we are meeting back an idea which is called Occam's Razor. So Occam Razor is a principle of philosopher from the 17th century, really a long time ago, I mean, older than me. And the Occam's principle was, when faced with different possible explanations, always pick the shortest explanation. So he was a philosopher, lived in the 17th century, and he already had this idea that when you have to choose between different explanations, always prefer the shorter explanation. And this is what this algorithm really proves that it works. Prefer short explanations. Because for short explanations, you pay a smaller penalty. So this is called the Occam Razor principle. And this is a principle that's being used widely as a guiding idea in science. If you have two competing theories to explain the motion of stars, you will prefer the one that is more elegant, that's more compact, that has less parameters and different exceptions, cases, and so on. So this is the Occam Razor principle, and we're able to prove mathematically a justification for some simple philosophical idea that was there for now 400 years. Okay, so after all this nice thing, what do I still owe you? In order to make sure that this description length can work as a weighting function, what are we missing? What? That it sums up to 1. I mean, I didn't tell you anything about these descriptions. And in order for this to work, I have to show you that it sums up to 1. Maybe it will not happen. So here we just need a very cute combinatorial idea. So we have to introduce one more requirement from our description language. So we will need to justify it, we'll need to assume that our description language is prefix free. So have you come across this expression before, prefix free? It's a requirement that we have in any programming language. We never want that one program will be a prefix of another program. So formally, what it means, we want to say that there exists no h different than h prime such that the description of h is a prefix of the description of h prime. Remember, the description of h is a binary string. The description of h prime is also a binary string. We don't want that one of these binary strings will be an initial segment of the other. And we have it always in programming languages. How do you make sure in a programming language that it's prefix free, that no program is an initial segment of another program?
Have a unique terminator.
Yeah, you have a unique terminator. So you know that when your compiler reads the program, it gets to the terminator, it stops reading. So it cannot be the prefix of another program, because in that case it will not read the rest of the other program. So this is a requirement which is very natural for programming language, that things will be prefix free. And now what I claim is that any description which is prefix free will satisfy this requirement. So we have a very cute claim here. So I have here a claim that says that if this function that goes from h to a binary string, so it's 0, 1, union over all lengths of 0, 1 to the m, is prefix free, then the sum over all h's in h of 1 over 2 to the length of the description of h is at most 1. And therefore, we will be able to use this as w of h, because it will sum to at most 1. So we need to prove this, and this is kind of a very okay. Well, I mean, I don't know how much time I have to enjoy this result, but just you can think of it intuitively. You can think of it like this: I have the empty string. So say I start with I will ignore the empty string. I have the string 0 and I have the string 1, and below them I have the string 0, 0 and 0, 1, and below this I have the string 1, 0 and 1, 1. And so on. Right? And now assume that I have a collection here which is prefix free. So I'm not allowed to pick. So I can go in my tree. I can go anywhere in my tree and pick. This is going to be a description. This is going to be a description. This is going to be a description. But those that are picked as descriptions have the requirement that none of them, this is not allowed. Because in this case, this guy is a prefix of this guy. So I have the tree of all possible descriptions, and I picked a description subset which is prefix free. So if I only pick these two, if I pick these two a description, I cannot continue. And here I have 1 over 2 to the 2 plus 1 over 2 to the 2. It sums up to less than 1. And if I don't pick this guy, then I can pick things below it, but then they will contribute less because they have shorter lengths. So I have 1 minute left. So actually, this claim doesn't have to do much with description lengths. It just says that more generally, any subset A, subset of the union over M of 0, 1 to the M, which is prefix free, satisfies this sum of all, say, A in A of 1 over 2 to the length of A is at most 1. And the proof is, half a minute proof, is that what I can do is I can generate all those strings by just flipping a coin. I'll start flipping a coin. And when I flip a coin the first time, it gives me either 0 or 1. Then I flip a coin the second time, it'll give me 1. I'll flip a coin. I'll keep flipping a coin. And I'll stop when I get to something which is a description. So now I can define the probability of any description of any h to be how likely will my coin pick it. That's the probability of every h. Since there's no prefix free, it's well defined. I'm flipping my coin. I'll stop when I get to a description. Every description can be reached because nobody will be blocked by another description. So it gives me a probability of all descriptions. OK? Now, what is the probability of a given? What if I give you such description? What is the probability that I'll pick it by just flipping a coin? Yes? Right. So it follows that P of h is at most 1 over 2 to the length of this description. Because the probability I'll pick a sequence like this by flipping a coin is 1 over 2 to the length of this. And the sum of these, this is just going to be sum to 1 at most because it's a probability. It's a probability of picking all descriptions. So the sum of the probabilities of all the description is at most 1 because it's a probability. That's basically the proof of this lemma, which allows us to use description lengths as a structural risk minimization. OK, have a nice weekend.